All right. Hello, students. This is a video tutorial on how to do the rocket project calculations. And I'm just going to walk you through step by step using an example of how to go about this. And so the thing that we're going to be calculating today are max height, time of max height, initial velocity, and theoretical flight time. Those four things are what you're responsible for calculating during this project. So let's start off with maximum height. And so the tools I'm going to use for this are going to be the 2022 data collection sheet. This is where we're going to be recording all of the maximum heights using the altimeter and the angle at which we measure during the rocket launches. And this first row right here, I have an example of what that data is going to look like. And this is data from last year that I collected from my rocket. And then if we go back to the actual calculation sheet that we're going to be working on, the symbols that we need to know are this symbol right here. That symbol, that little weird circle with the line through it, that's called theta. That's going to represent our angle from horizontal. And then X is our horizontal distance from the launcher. And then Y is our maximum height. And what we're actually going to be using is SOHCAHTOA to actually figure out what our max height is. So as a reminder, SOHCAHTOA deal with sine, cosine, and tangent. So is sine, and that is equal to the opposite over hypotenuse. Ka is cosine, and that's adjacent over hypotenuse. And TOA, which is tangent, and that's opposite over hypotenuse. So important measurements that we need to know about to figure out our max height is the height of our inclinometer is 4.75 feet, and that our inclinometer is exactly 200 feet away from our launcher. And so what I'm going to do is actually click on this right here and go ahead and go to my data collection sheet. And this is where I'm actually going to find the numbers I need to know to do my rocket calculations. So if we go down to number 1, it says draw a picture of the right triangle for the height of our rocket. What I'm actually going to do is I'm going to draw the inclinometer right here. This is our tripod, and this is what we actually used to measure the height of the rocket. And I'm going to draw my right triangle from here. Here is my right triangle. And this proportions of this right triangle isn't exactly perfect, but it's just there to give us an idea. We know this angle right here is going to be 90 degrees. And then I'm actually going to look at my data collection sheet to figure out what this angle is right here. And if we look at that, our angle is 48.3 degrees. So I'm going to put 48.3 degrees in here. And we know our horizontal distance from the rocket launcher is going to be 200 feet. One thing I do want to note is the height of our inclinometer matters. And so this height of the inclinometer, that's going to be 4.75 feet. And what I'm trying to find is our maximum height. And I'll call that Y for maximum height, but this is what I'm trying to find right here. This is our goal. So we just did part 1 of just drawing the picture and getting an idea of what we're actually calculating. And so for number 2, it says use SOHCAHTOA to calculate the max height. And as you guys remember, SOHCAHTOA uses opposite, adjacent, and hypotenuse. And so what I'm going to do is just label the opposite, adjacent, and hypotenuse. So this is our angle right here. The side that's next to our angle is always our adjacent. So that's our adjacent. the side opposite of that angle is going to be our opposite side. And then the longest side, or the side that's opposite of the 90-degree angle right here, that's always our hypotenuse. And so now I have a choice here. What function am I going to use? Sine, cosine, or tangent? And as a reminder, the things that we know right here is we know what theta is. That's going to be 48.3 degrees. We know what our adjacent is. That's going to be 200 feet. And what we don't know is our opposite side. And that's what we're trying to find, is the opposite side. So which one of these functions, SO, CUT, or TOA, uses the adjacent and opposite? And so if I run through this, sine uses opposite and hypotenuse. That's not what we want. Cosine uses adjacent and hypotenuse. That's not what we want. So that leaves us with tangent, which indeed uses the opposite and adjacent sides. And so the way we're going to do this is write out tangent, put our angle inside that tangent, and then set it equal to the opposite over adjacent. And so we're calling the opposite side y. So I'm going to do y divided by the adjacent side, which is 200. So that's what I have set up right here. And then our last step to figure out what our maximum height is to solve for y. And so I'm dividing by 200 here. And so to get the 200 to the other side, we need to multiply by 200 on both sides. And that leaves us with y equals 200 times tangent of 48.3 degrees. And if we bust over to Desmos, we can figure out exactly what that is. All right, so while I'm working in Desmos, the thing that I need to be careful of is whether I'm not in radians or degrees. So what I'm going to do is actually go over to the graph settings and default its radians. I'm going to switch it over to degrees. I want to be in degrees. And then I'm going to type in what I solve for, 200 tangent of 48.3 degrees. And that gives me a max height of 224.47 feet. So y equals 224.47 feet. And that is our max height. And then one more thing I want to add about this, it's not quite done yet. This 224 does not account for the height of the inclinometer. And so to figure out the actual max height, I need to add this number to this number, which should be 229.1-ish. So that is actually our max height, is the 229. So we just did part 1 of our calculations for the rocket project. For part 2, what we're trying to do is figure out our time of max height. And so just to review the symbols of this problem, we're calling t, which is kind of our x in this situation, that represents time in seconds. And then what we're going to need to know is frames per second, and FPS stands for frames per second. And one thing of note is the iPhone we're using to film the rockets shoots at 30 frames per second. And so what I need to do is go ahead and click on this link right here and go to the data collection sheet. And I'm actually going to click on the link to this video right here. myself for a second. Awesome. So all the videos are uploaded at a good quality. And so sometimes it's really hard to see the rocket. So I would change the quality to the highest you can do before you watch the video. And at this point, it might be advantageous for you to download the video so that you can count the frames. All right, so here's the video of the rocket before it launches. And so what I'm going to do is figure out what the time of max height is by counting the frames. And so I'm going to just cycle through the frames by pressing my arrow keys and waiting until the rocket starts to launch. Okay, so that's when it starts to launch right there. So I'm gonna go back until that first frame right before it launches, and I'm gonna count the frames until the rocket reaches max height. So there's the rocket at max height, and I counted 67 frames for that to reach max height. So I'm gonna write that down on my sheet down here. So 67 frames equals the max height. And so to figure out what time 67 frames is, what we're gonna do is just a simple unit conversion. So if I take any number of frames and multiply this by my unit conversion factor, I can figure out how much time there is. And so our unit conversion factor, what I mean by that is we know that an iPhone shoots at 30 frames per second. So for every second, the phone shoots 30 frames. And so what I'm gonna do is multiply by 1 second, divide it by 30 frames. And you can think of this frames as frames divided by 1. And what happens is I have a frames on top and a frames on bottom. And when I multiply this, these frames cancel out and I'm left with just seconds. And so what we found in our video was the max height was at 67 frames. So I'm gonna take 67 frames and multiply that by 1 second divided by 30 frames. You can think of this as 67 over 1 because any number divided by 1 is itself. And if I multiply these across, then this is the same as 67 divided by 30, which is 2.23 seconds. Awesome. So we just did that unit conversion. We found the time of max height. And we calculated the max height to be 224 feet. And I know now that at 224 feet, the time that went by was 2.23 seconds. It took 2.23 seconds for the rocket to reach max height. And to find the total flight time, it's going to be different in real life than our theoretical total flight time. But to do this, all I'm going to do is go back to my video and continue to count the frames. All right, so after watching the video, I counted 360 frames for the total duration of the flight. And so I'm going to do the same thing I did earlier. I'm going to take 360 frames, and I can put that over 1, times 1 second over 30 frames. That's the same as 360 divided by 30, and that is 12 seconds. And that is my total flight time for my rocket, is 12 seconds. And that includes the parachute. So at this time, we are done with the time of max height, which means we are ready to calculate the initial velocity. All right, so the symbols that we're going to be using for the initial velocity, this is v sub 0. That means that's the v naught. That's what the symbol we're going to use for initial velocity. H of t is going to be the function that represents the vertical position given time. And then t is time in seconds. And then g, that's what we're calling gravity. That's going to be 32 feet per second squared. And then this y naught is going to be our starting height of the launcher. All right, and then the formula that we're going to use is going to be from your kinematic equations, and that's h of t equals -1/2 times gravity times t squared plus v naught times t plus y naught. And what we're trying to figure out is our initial velocity. That's this simple right here. And so this first part of this problem for calculating our initial velocity is we're going to write down our known variables and our constraints from the symbols above. And so the thing that we're going to be using is the max height and the time of max height to figure out what our initial velocity is. And so we already figured that out earlier. Our time of max height is going to be 2.23 seconds. So I'm going to put 2.23 seconds in for my time. That's what I know. And gravity, we know, is 32 feet per second squared. And I got that from above here. That's given to us. Y naught is the height of the launcher. And that may differ from what launcher you decide to use for your rocket. We have two different versions, but the height of the launcher that I'm going to use in this example is going to be 1.5 feet tall. That's the height of the launcher. And so V naught, this is what we're trying to find. This we don't know yet. But H of t represents the vertical position given time. And we're using max height here. And we already found our max height to be 224.47 feet. So I'm going to write 224.47 feet for our max height. And so at this point, we're going to use the max height and the time of max height and solve for the initial velocity. So I'm going to use this formula as my tool first. So H of t equals -1/2 g times t squared plus v naught times t plus y naught. And all I'm doing here is plugging in my knowns from here. And so H of t, we know, is 224 feet, 0.47. So I'm going to do 224.47 right here. And that's going to be equal to -1/2 times gravity, which is 32, times t squared. Our time is 2.23. So I'm going to plug 2.23 into here, and that's squared. And then we're going to be adding our initial velocity that we don't know yet. So I'm going to leave it as V naught. That's what I'm trying to find. Times our time again, which is 2.23, plus our height of our initial launcher. And that's going to be plus 1.5. So at this time, all of these are just numbers. The only unknown here is this V naught right there. That's what I'm trying to figure out. So let's simplify this before we solve for V naught. So if I look at this, I'm going to start here. Half of 32 is 16, and then we have a negative sign. So this is the same thing as negative 16 times 2.23 squared plus v naught times 2.23 plus 1.5. And this is still 224.47. And so what I'm going to do next is just multiply 16 times 2.23 squared. Get rid of this here. Negative 16 times 2.23 squared. That's going to be negative 79.56. Cool. And then what I'm going to do is I'm going to combine like terms here. I can combine these two numbers because they don't have a variable attached to them, which means they can be the same thing. And so negative 79.56 plus 1.5 is going to be negative 78.06 plus v naught times 2.23. And that equals 224.45. All right, so the next step I'm going to do here is I'm going to add this over to get this by itself. I'm eventually going to divide 2.23, but first I need to get this over to the other side. I'm going to do that by adding 78.06 to both sides. $224.45 plus 78.06 is going to be 302.51, and that's going to be equal to v naught times 2.23. So my last step here to get v naught by itself is going to be dividing by 2.23. I'm going to divide by 2.23 on this side. Those cancel out on that side, and then I'm left with v naught. So v naught is equal to 135.65. And this is feet per second. So right when the rocket leaves the launcher, it's going 135.65 feet per second, which is pretty fast. And so that concludes this part of the rocket project calculations, which is the initial velocity. And now for the last part of the calculations, the theoretical flight time. And so the tools that we're going to use is we're going to use our initial velocity, the vertical position formula, which is h of t, time, t equals time in seconds, gravity is still the same, it's still 32 feet per second squared, and y naught is our starting height. And this is our formula right here that we have. And we now have a completed formula that models the rocket's flight given time. The tools I'm going to use is I have a link to a quadratic formula calculator that's a spreadsheet that you just plug in A, B, and C for, and it spits out your zeros. And then we'll go from there. So the first part of this is we're going to be recording our height given time formula right here for this first question, denoted as h of t. So what I'm going to write is h of t equals, and then plug in all of the things I know. And so this is the height formula here, but I'm just going to plug in all the stuff I know. So this is minus 1/2 times gravity, which is 32. And then we have a t squared. That's going to be staying as t squared. Plus our initial velocity, which we calculated earlier, which is 135.65 times t. And then lastly, we're going to be adding our start height, which is y naught, and that's 1.5 feet. So this right here is the formula that describes our rocket's height given time. So our next step is we're going to actually plug in our formula into the quadratic formula and just write it out below. And so to do so, we're going to need to know what our a, b, and c are. So a is always the term in front of the x squared. We don't have x's in this formula. We have t's. That's fine. Same thing. And the number that's in front of the t squared in our formula is negative 1/2 times 32. So this is negative 1/2 times 32, which is the same thing as negative 16. So a is equal to negative 16. B is always next to the x term right here. And our x term is this just t by itself, and that's 135.65. So I'm just going to do 135.65 right here, and that's our b term right there. And then lastly, c is always the number that's always by itself and doesn't have a variable attached to it, like x or t in this equation. Our c is 1.5. And so to actually finish this question, what I need to do is plug this into the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so I'm going to just write out x equals negative b. Our b is 135.65, 135.65, plus or minus the square root of b squared. So I'm going to take 135.65 squared minus 4 times a, which is negative 16, times c, which is 1.5. And that's all under the square root. And then I'm going to take this entire thing and multiply it 2 times my a term, which is negative 16. And boom, that is my answer for this part 2 of the theoretical flight time. At this point, I'm going to go ahead and use the quadratic formula calculator and plug in my a, b, and c to find which one is my actual flight time. And so here's the quadratic formula calculator. And as a reminder, our a is negative 16. Our b is actually 135.65. So I'm going to plug in 135.65 in there. And then our c term is 1.5. And so I got 2 different numbers here. I got negative 0.01 and 8.49. And I'm going to record that down here. Negative 0.01, and then x equals 8.49, and I apologize, these are t's. And so which one of these zeros represents the theoretical flight time of our rocket? And what I want you guys to observe is this graph here. What the quadratic formula tells us are the 2 places where the curve crosses the x-axis, right there and right there. However, the horizontal axis represents time. And so one of our times is negative. And we can't really go back in time. We can't really have negative time. So what we're going to actually do is exclude that, because our time starts at t equals 0, not t equals negative 0.01. So our start is actually right where it crosses the y-axis, which we know is 1.5 feet. And so our flight time is from 0 to that other 0, which is 8.49. So our total flight time is actually equal to our total flight time equals 8.49 seconds. And I want to emphasize that this is the theoretical total flight time. This accounts for the flight time if we didn't have a parachute and there's no air resistance. And if you guys remember, our actual total flight time was 12 seconds, which makes sense because our parachute slows down the rocket as it falls from the sky. And so that concludes all of the calculations that you will be doing for the rocket project.